Hi everyone, welcome to Low Power Image Classification with the BrainChip Akida Edge AI Enablement Platform. I'm David Tischler, a developer program manager at Edge Impulse. Let's take a look at our agenda for the day. First, I'll cover who is Edge Impulse. Then I'll be joined by Josh Buck, our senior silicon solutions engineer, to give an introduction to the BrainChip Akida processor and Edge AI Enablement Kit. Next, I'll give an overview of the project we'll be demonstrating today. I'll walk through how to build an image classification computer vision model in Edge Impulse, and we'll take that model and deploy it onto the Akida Enablement Platform. We'll finish with a wrap-up and conclusions on possible next steps in a journey from prototype to production Edge AI devices. But first, let me cover two quick items to get us all on the same page. What we're going to build today is a project covering a medical use case, but the concepts we discuss can absolutely be translated to other domains and industries. So my first definition is the type of computer vision we'll be performing, which is image classification. You might be familiar with computer vision that shows bounding boxes around an object in an image or video stream, but we're more interested today to determine what is contained in a picture. Like this example image here. This is simply classified as a plant. We don't care too much where in the image it is, and there may be other artifacts in the picture like a pot, some dirt, a wall, the floor, or other items. But ultimately, this is a picture of a plant. And the second definition is to clarify what we mean by Edge AI. There are actually quite a few definitions of Edge AI floating around out there that I've come across, but here we're going to be talking about a machine learning model that is running entirely on a device with no connectivity back to the cloud needed to make a prediction. Now, the model does need to get onto the device somehow, and that could be via a flashing process at the factory, simply placing a model onto a USB stick and copying it to the device, or if there is internet access, then the model could be downloaded from the cloud. But ultimately, once that model is on the device, no matter how it got there, the connection or connectivity back to the internet is not required for it to run inference. The first item on our agenda today is who is Edge Impulse? At Edge Impulse, we help you to build, train, and optimize Edge AI solutions. We look at Edge AI projects through four basic components or functions: collect, design, test, and deploy. In our example project today, we're going to do X-ray image classification. So in practice, that means we will import a professionally curated data set, build a model that can recognize pneumonia in an image, measure the accuracy of detecting pneumonia, and then deploy that model onto the BrainChip Akida Enablement Platform. Looking a little bit closer, first is collection. We're going to use an existing professionally labeled data set of X-ray images and bring it into Edge Impulse. But you can also import existing data from Amazon S3 buckets, Google Cloud, or other locations. And we'll use images today, but Edge Impulse also supports audio or sensor data. In the case of audio, that could be for doing keyword spotting or wake word detection, or if you're using sensor data, that could be for temperature and humidity, motion detection, or similar. Next is design, where you'll define and build your machine learning model. And this is done via processing and learning blocks. And there's a variety of back-end architectures such as YOLO, MobileNet, NVIDIA Tau, and more. In the testing phase, you can ensure that your model is working as intended before deploying it onto devices. You can test with live images coming from a camera, or you can use a set-aside portion of your data set that's not included in the model creation phase, so it's unseen by the model. Finally, in deployment, you have the option of building ready-made firmware for a wide variety of devices or generating libraries to plug into your existing application framework. We're going to use the BrainChip Akida today, so I'll walk you through that process. With that background, though, let's explain a bit further what I'm going to show off today. As I mentioned a moment ago, I want to explore the ability to build a computer vision model that can identify pneumonia in an X-ray image of a patient. My goals are to take an existing professionally curated data set, Build an accurate, low power classifier that can assist, probably not replace though, doctors in real time. For that, I want to understand the time required to classify an image. How long is it going to take to feed in an X ray image and get back a prediction? I want to understand how much power that's going to require. And I, of course, need to know how accurate is that classification. And then finally, as mentioned, I'm going to deploy it onto the Akida development kit to test and demonstrate the feasibility of this. In the end, we should come away with something that looks like this. Take an X-ray image, plug it into our model, and come back with a prediction, understand the power that it took to do the prediction, and how long it takes. Now that we've seen what the Edge Impulse platform is at a high level, let's take a closer look at the Akida neuromorphic processor included in the Edge AI Enablement Kit. For that, let me introduce Josh Buck, our Silicon Solutions Engineering Manager, to cover this a bit deeper. Welcome, Josh.
Thanks, David. I'm glad to be here. Let me give you a little bit of detail about what's inside and under the hood of the AKD 1000 by BrainChip. As we know, BrainChip's a neuromorphic design processor, which is really great for Edge ML applications. It brings a lot of benefits into Edge Impulse by expanding the platform to very low power designs, and they offer many different ways to interact with their devices. Centered around all BrainChip's technology is the Akida runtime engine and the Akida chip itself. The Akida is able to take in many different kinds of sensor inputs and do inference against them, and give you those inferencing results in a very low power manner. Many of the examples we have on Edge Impulse include vision applications, including keyword spotting as well for sound event detection. And then we've also added the ability to take in accelerometer data and do predictive maintenance applications as well. And this is just the beginning. You can really interface any sensor with the Akida device. Behind the scenes, not behind the scenes, but also we have from BrainChip many different examples and ways to get started with Akida. So just like how Edge Impulse provides our users the ability to, work very quickly with Edge Impulse Studio and get a model trained on device, BrainChip offers this for Akida. So they have many different examples for data pre-processing and model training, and then as well as to visualize different outputs. They work with many different applications and coding interfaces like Keras and TensorFlow and Python. And they also have Jupyter notebooks for ease of use as well. Many of these examples all are enabled to run on the Akida device. And so you can go and take a look and see, how much power and how quickly inferencing is run, including the accuracy for the models. And then they also have a model zoo for them to just immediately get started and just see something work. Once you have an example running, or you've been using Edge Impulse to get something working for Akida, really what's going on behind the scenes is that Edge Impulse is built on top of the Akida model API and Akida runtime engine, right? We have the ability to do software and simulation, so you don't even have to have an Akida device to at least get some simulated results, right? And if you have one of their enablement devices, which usually includes this PCIe device that has the AKD 1000 on it, Edge Impulse sits on top and calls into the Akida API and runs the model inferencing on device. Those who have gone the IP route and actually integrated the Akida AKD 1000 into the Silicon IP also take advantage of the same kind of technology and same software stack, right? So we're still calling into the engine library. We're also still using Akida for that inferencing, but now you're really taking advantage of that low power ability since you're integrated with the device. So how does all this work, right? What is neuromorphic like, and what are we doing here with Akida? Well, in a typical frame-based convolution, represented here on the top, right, you might have to have a number of different operations to process and perform these convolutions, right? So if you take one that maybe is a 9 by 5 by 5 convolution, you might have to do 225 max. Okay, that's a lot of operations for something that may be very sparse and may not have a lot of actual value in it, and just a lot of zeros in that matrix or in that tensor. But with Akida, we're actually working on events-based convolutions. So we really only process the data that's actually of importance, right? So we look at a different frame and we process a different kind of convolution. And in the end, we're only actually operating on the 9 by 3 grid that matters. In this case, we're only doing 27 max. And because you can do less operations and still get the same computational results, right? You're getting a lower power benefits and increased speed in your operations. Akida 1.0 is chiefly working with the AKD 1000. It supports a number of different keras layers and different model types and different operations, typically fully connected and convolutional types. BrainChip is also coming out with the the Akida 2.0, and it has much, much more capability and is going to greatly expand the type of models that you can run on these devices.
Awesome. Thanks, Josh. Appreciate the deep dive there into the Akida. Next, we'll go ahead and cover what type of a project I've built. I'll show off the image classification that we've done and how to use the Edge Impulse platform. Thanks. Now that we better understand the Edge Impulse platform and what hardware we're using, let's return to our project and identify what we need in order to build this. If we want to be able to predict if an X-ray contains something that indicates a patient has pneumonia, then we need lots of images of patients that do not have pneumonia, which we'll call normal, and lots of images of patients that do have pneumonia, which is what we'll label those as. We also need a doctor, or at least someone who is very specially trained and can use some secondary testing data from a patient to be able to identify which is which. At first glance, to my untrained eyes, I can't tell the difference between normal X-rays and pneumonia X-rays. Fortunately, though, this does already exist and was made public as part of a research paper written a few years ago by doctors at UCSD. This link shown here contains nearly 6,000 professionally captured and sorted X-rays made available as a zip file to download on Kaggle. So that's exactly what we'll do, is download it. Now that we have a data set of images, we can build our classifier. To do that, we'll create an Edge Impulse account, which is free for development purposes, and there are enterprise plans available for teams that need more powerful training, collaborators on projects, or custom training blocks. But you can definitely get started with either the free plan, or there's also a free trial on the enterprise plan that you can use as well. Once you're logged in, you'll create a project and simply give it a name. The first thing we'll do then is upload our data set that we just grabbed from that link shown a moment ago. Click on Data Acquisition on the left, click on the Upload button, and then you can choose the files or folders you want to upload. The best strategy for this project is to unzip the zip file we downloaded from Kaggle, and you'll see it has a normal folder and a pneumonia folder inside of it. So that makes it easy because you can just choose the normal folder, set the label to normal, and upload all 2,600, maybe 2,700 or so images in one click. Then just do the same for the pneumonia folder. When it's finished, you'll see you have about 5,800 items in your data set, labeled and ready for use. Moving into impulse design, we'll start the process of building our ML pipeline and creating the neural network. I've selected an image block and a BrainChip Akida classifier block, and we can see the two labels here in the output features, normal and pneumonia. I'll click Save Impulse, and before I move on further, I just want to point out that everything I've shown so far and what's coming up next are all documented and available at docs.edgeimpulse.com. Explanations, concepts, how-tos, device-specific instructions, it's all there to review as needed. Coming back to our pipeline, next up is feature generation, where features are extracted from our data before being fed into the training process. You get a nice visual representation of how the features cluster in two-dimensional space, and this occurs for sensor data and audio projects as well. Once we make it to the classifier block, it's time to perform the actual model training. You can configure the number of epochs you train for and the learning rate, and further down, you can manipulate the network layers, drop out, and choose from the various architectures that are available. You just have to click Start Training when you're ready, and the process begins. With almost 6,000 images in this project, it might take a little while to train, especially depending upon how many epochs you train for. But once it finishes, you come away with a confusion matrix, accuracy measurement, and another visual representation, this time showing correct and incorrect predictions on the validation data. I ended up with an overall 94.9% accuracy, but I'm likely overfitting pneumonia a bit here at 97% accuracy, while normal is lower at 87%. Ideally, I would spend more time here fine tuning this a bit, but it's worth noting that it's probably better to incorrectly predict pneumonia when in fact there is none versus predicting normal when pneumonia is actually present. But our goal is not to replace a doctor, and as a demo, I'm going to accept these results and move on. Productization or final end user devices of any AI technology really need to have more work done in this phase to ensure the best possible outcome. Also, looking at the feature explorer here on our X-ray images, there's quite a bit of overlap. But if you notice on this screenshot that I've brought in from a different project, one that's motion-based, you can see how the data will sometimes separate itself into distinct buckets, making final products more reliable. Moving on, we're almost ready to give our model a try, but before we get our Akida kit turned on, we'll do a quick model testing. When we uploaded the data into Edge Impulse earlier, a portion of the images were set aside, and they weren't used during the model creation we just did a moment ago. Instead, the images were saved so that we can use them now. The model has never seen these X-rays, so this is a great way to quickly see how accurate it is on brand new images. You can click on any individual sample to inspect the results of the classification, or you can also test the model on live data from your device. But I don't have the Akida box turned on and running quite yet. That's next. Taking a peek back at our agenda, we've made it through quite a bit. We talked about Edge Impulse, the BrainChip Akida, described our project and goals, and now we just went through the dataset, training, and testing of our model. Now we're ready to get our Akida Enablement Platform up and running. The first thing I want to do is build an Akida optimized deployment package from the Edge Impulse Studio. On the left, click on Deployment, and you can begin typing the word BrainChip into the search box to narrow down the choices for Akida. My particular hardware is the Linux AArch64 with AKD1000 mini PCIe card, so I've selected the one in the middle. But if yours is different, simply choose the one you need. This will build a package and download it to your laptop or desktop in a zip file. Inside that zip file is the model, and if you remember all the way back to the beginning, we defined Edge AI as not requiring internet connectivity, but we do need to get this model onto the BrainChip hardware somehow, so you could just copy this over to the device on a USB stick. However, in my case, I do have Wi-Fi available, so I'm just going to leave this file alone. Mostly, I just wanted to get our model build complete in advance of the next step. It's also worth pointing out that the Raspberry Pi Akida Enablement Platform that I'm using has all the ports and interfaces exposed, so you could run what I'm about to show right from the device's desktop with a monitor, keyboard, and mouse attached. In my situation, I'm going to go with a bare minimum installation of Ubuntu Server and just SSH to the box instead though. Once an Ubuntu Server SD card is flashed and booted, you just have to install the Akida PCIe driver and the Edge Impulse CLI and Linux SDK. Setup instructions for each of the various enablement kits are available on the BrainChip website, and the Edge Impulse installation instructions are over in docs.edgeimpulse.com, as I mentioned earlier. Once everything is installed, you can SSH to the kit like any other Linux device. To run our model, we have two choices. The first one I like because it's closer to the native development process that needs to be followed for a real world deployment, where the model is just one component and it needs to be integrated into an existing application or software stack. A doctor needs to have some sort of GUI and interface that they're using while in a laboratory, a clinic, or a hospital. Running a simple Python 3 classify image.py with the location of the model and the location of the image to classify will print out a prediction result and also give the inference time taken. However, this isn't very visual, so let's check out another option. The second choice is to hook up a USB webcam to the box and run Edge Impulse Linux Runner from the command line. This will start up a lightweight web server on the device and broadcast the output from the camera on the local IP of the box. This makes for a nice visual demonstration, but has a few considerations to keep in mind. First, are you aiming the camera at a physical X-ray, like the actual X-ray that you hold in your hand? If so, what's the level of lighting that's behind the X-ray to backlight the X-ray image? Does it match what the model was trained on 6,000 times, almost 6,000 times? Similarly, if you're aiming a camera at a monitor that's displaying a render of the X-ray, is the image being zoomed? What's the monitor's brightness and contrast? Now, to be fair, the same does go for native inference via Python, because if you train a model on what is ultimately someone else's data set, but then deploy it into your own local conditions, your model may suffer from diminished accuracy. So back to our earlier discussion about productization, that's another factor to consider. And that goes for any project, any use case, or any industry. The final item on our agenda is to evaluate our results, have a closer look at what we discovered, and consider what some potential next steps might be. We successfully built and deployed our model, but let's review what we set out to accomplish. We wanted to understand the feasibility of building a pneumonia classifier that could assist doctors by learning about the time needed to evaluate an X-ray, the power required to run the Edge AI model, and find out what type of accuracy we could achieve. The Akida Enablement Platform actually told us 2 out of these 3 items if we zoom in a bit. When using the web-based interface below the image view, if we look close, we can see that on this particular image, we came in just under 100 milliseconds to perform the classification, and we used 0.76 milliwatts to run that classifier. And if you remember from the neural network creation step, we achieved 94.9% accuracy, albeit with some room for fine-tuning, perhaps trying to improve our normal classification a bit while dropping down that possible overfitting on pneumonia. Ultimately, though, we demonstrated that X-ray classification works. And we demonstrated very low power consumption with nearly real-time inference results. And we ran the model on the device with no cloud connectivity. Of course, as I mentioned a bit ago, we only focused on the machine learning aspect here, and application development was out of scope. You would still need to consider the bigger picture of how does a doctor or non-technical user actually interface with the system? How do you tie an X-ray to a patient? Where are the images stored? And are they stored in a secure manner? And so forth. There's also the process of actually needing to take an X-ray and develop it, and that may not be totally seamless or rapid, depending upon where this system is being leveraged. Coming back to the hardware, we also need to keep in mind that we used a development kit. The Akida Edge AI enablement platforms make it easy to prototype, but this hardware turned out to be far more powerful than we actually needed. If we're getting a prediction in 1/10 of a second, then maybe we could make do with something smaller. And this box is not huge, but if we were to productize a solution and build a dedicated device for this sole purpose of X-ray classification, then sell it as a turnkey solution in the medtech market, we could significantly lower our bill of materials by eliminating everything not necessary. Even better would be to build a custom PCB and wire the Akida processor to the host CPU directly via traces. Or if you really want to lower the power envelope required, BrainChip also licenses the Akida IP. You could use off-the-shelf ARM Cortex-M cores and spin your own MCU with integrated Akida cores and build a device that lasts for days or weeks on battery power alone. Finally, we touched upon this earlier, but what we've done here can certainly be translated to other industries, use cases, or applications as well. Industrial, construction, agriculture, smart city, retail, they all have use cases where image classification can help drive business or lower costs. Generally, at this point, I would field questions from the audience, but as we pre-recorded today's webinar, I'd instead recommend posting any questions you come up with over on our forum at forum.edgeimpulse.com. We monitor the forums regularly, and we do our best to respond to community questions as they come in. So be sure to drop any issues or comments you have there. Lastly, you can see here the link to purchase an Akida platform is simply shop.brainchip.com, but I'll put the link in the video description down below as well. Thanks everyone, and have a great rest of your day.